All right, guys, let's begin. This is, we're going to continue on the topic of convolutional neural networks. Uh, how did we define convnets in the last class, Lakshay? Yeah, what do convolutional neural networks do?
They scan the input.
They scan the input for patterns because you want?
Invariance to position.
You want position invariance. But where did these models originally come from? They didn't come from that perspective. So to see where they, how these things originated, we're going to go back and look at cats. So for the longest time, people have been wondering what the process is between your eye and your brain. How do the images in your eye actually end up resulting in your interpreting the world in a visual manner? And so we've been studying it. And much of the early research sort of focused on behavioral studies. How do you respond to visual stimulation? How do you compose stuff? So things like Gestalt. How many of you see the picture to the very left? What is that? Do you actually, is there really a cube? No, right? Just a bunch of little circles, Pac-Man figures. What about the second figure? What is that? It's a collection of patches, right? And the one to the extreme right, that's the nicest one. It looks like something from a torture chamber in a dungeon, but it's just a bunch of triangles. So your brain is filling in the rest. And this is what we call Gestalt, where your perception is actually sort of surpasses what you actually sense. And people spent all their time studying these things, but it still gives us no idea of how the brain actually achieves what it does. For that, the first study was by these guys, Hubel and Wiesel, and this was in 1959, where they studied cats. It was called Receptive Fields in the Cat's Triad Cortex. Now, our human eye is a classical example of poor design. So if you ever want, if anybody ever tells you that, we are the outcome of intelligent design, whoever designed us wasn't very intelligent. Your eye, for instance, starts off with sensors, and then the retina falls behind the sensors. So the sensors have to sort of punch a hole through your retina to go to the back, which is why you have a blind spot in your eye. But then how does the processing continue? You'd expect that, as soon as it passes the eye, it begins processing things all the way to the back. Nope. That connection goes all the way to the back of your head, and then the processes come forward from the very back. So this is what we call the V1 portion of the visual portion of our brain. The equivalent in cats is the striate cortex, so-called because the cells are striated. And so what these guys did, they ran some experiments on the striate cortex of the cat's brain, which is the first spot where the neural signals from the eye land. They got 24 cats, not these ones, but they must have looked like this. They anesthetized them, immobilized them, put them on artificial respirators, and this anesthesia was delivered using truth serum. They stuck electrodes into the brain. They very cleverly do not tell us if the cats were killed afterwards, but they do tell us that the brain tissue was studied. So I leave that to your imagination. Anyway, what did they do? The cat was anesthetized. They kept the iris open artificially, and then they beamed light into the eye to see how the retinal cells and the cells that the electrodes were connected to in the brain responded. The light itself had different wavelengths, and they were beamed at it in different patterns. Basically, they took a spot and they moved it in different directions to see how the cells responded. And here's what they found. So each cell responds to a small region of the retinal area, not to the entire region. But within the retinal area, it has inhibitory regions and excitatory regions. So when light falls on the excitatory region, the cell glows. But regardless of what happens in the excitatory region, if there's any light in the inhibitory region, the cell does not. So if you have diffused light, the inhibitory and excitatory regions cancel each other, there is no response. But if you actually begin studying how the cell responds, they found that the cortical cells have responses of this kind. So here the blue region is where you have high response, the red is where you have inhibition. And so what you see is that all of these cells seem to respond to linearly oriented patterns of light, where the orientation itself could be different for different cells. And here's one of the pictures from their paper. So in this case, they were just taking a light and moving it in different directions. So when the light moves left to right, for this particular cell, there is no response at all. As you rotate it, when the pattern is vertical, you see lots and lots of responses, but then as it continues to rotate the cells, the response dies off. It doesn't have to be even a complete pattern. It can be just movement in one direction and the response stays much the same. So basically, oriented slits of light were the most effective stimuli for activating the striate cortex neurons. Basically, the eyes, the sensors in your brain respond to little vertical and horizontal and angular patterns of linear patterns of light. But then there's more to it. In a later paper, they showed that within the striate cortex, there are actually two levels of processing. The first level of processing was what they call S cells or simple cells, which responded to these oriented patterns of light. And the second level of processing was by these so-called C cells, which stood for complex cells, which cleaned up the response of the S cells. So this is going from bottom to top. Within the retina itself, each cell responds to a circular pattern. But the S cells were connected to linear arrangements of these retinal cells. And so an S cell would respond if light followed a linear pattern on the retina. But then S cells are kind of sensitive. So if you have some noise, the S cell could fire. To clean this up, you have the C cells where each C cell connects to multiple S cells and and reflects the response of the strongest response of any of the S cells that it's connected to. So if a C cell is connected to 10 S cells, it's just going to reflect whichever of the 10 has the highest response. And in this manner, it sort of cleans out any local perturbations that may be the outcome of noise. So complex C cells build from similarly oriented simple cells. They fine-tune the response of the simple cell, but then you actually have layers of these. You have S cells, which correspond to linear patterns, C cells, which clean them up. Then you have other additional S cells, which look at the output of the C cells themselves and find patterns in those. And then you have C cells connected to those S cells, which clean up their response and so on. You have a hierarchical buildup of patterns that these cells respond to. And they show that as you go through the brain, through the various layers, the patterns the cells respond to become increasingly complex. They continue their experiments later on monkeys, and so we won't go there. We'll stop with cats. But anyway, so that was the biological motivation. That's exactly how we found, how they discovered, or they hypothesized the mammalian cells, the mammalian visual system worked. And of course, their work was incomplete. They said this model cannot accommodate color, spatial frequency, and many other features to which neurons are tuned. So the exact organization of these cortical columns remains a hot topic of current research, and it still does. But before we continue, here's a poem. So this is a simple one. I'm giving you 10 more seconds.
When they design convolution networks, what's this, the motivation?
We'll get to that. So what is the answer here? The first one, right? S cells find patterns and C cells clean them up. Anyway, so this is 1950 something, 1960s. Fast forward 2 decades. This dude, Kunihiko Fukushima, began designing computational models for what Hubel and Wiesel had come up with 20 years earlier. And he realized that there was one little flaw, at least one flaw, that remained in Hubel and Wiesel's model. And this has to do with the so-called grandmother cell. How many of you have heard of this? So in fact, have you heard of the Jennifer Aniston neuron? No. Now, these neuroscientists like to study people who have epilepsy. They're a fantastic subject because they go in for treatment and the doctors open up their skull. They have lesions on the brain. And so they lie there for several days with their brain exposed. And so these guys go in there, predators, they stick little meshes of electrodes on the brain and then show these people various patterns to study neural firings. And they found that in one particular pattern of patient, there was a cell that only responded whenever this person was shown pictures of Jennifer Aniston. So this is the famous Jennifer Aniston neuron. It's there. There's a nice Nature paper about it. It turns out that every one of us has these individual cells that respond to specific things. We have a cell that's going to respond anytime we see our grandmother. But the thing is, this cell will respond regardless of whether your grandmother is in front of you or out to the side. It responds to the presence of grandma and not to the position of grandma. And that's something that Hubel and Wiesel's model didn't really fully capture. So Fukushima came up with a computational model derived on Hubel and Wiesel studies. And the one that we will look at is called the neocognitron. Clearly, anytime you have a neo something, there must have been an earlier something without the neo. So I'm assuming that there was a first model called the cognitron, and then V2 was the neocognitron, my assumption. But here's what the model looks like. It says that the visual system consists of a hierarchy of modules, where within each module you have two sets of cells. The first are the S cells, or the simple cells, based on Hubel and Wiesel's model. And these are followed by C cells, or the complex cells. So the S cells respond, and the whole thing is arranged in a hierarchy. So you have one collection of S and C cells. The first one responds directly to the retina. The second collection of S and C cells responds to the outcome of the first layer. The third set responds to the outcome of the second set, and so on. So it's hierarchical. Of these, only the S cells are learnable. They're plastic. The C cells have a fixed response. And how does the whole thing work? So within each set, the S cell, what they call the within each module, the S cells were arranged in planes according to his model. So I'm sort of drawing them at an angle. Okay, let me draw it face on. So the S cell is arranged in planes, where within each plane, you have several S cells which all have exactly the same response. They respond to the same patterns. So what is the distinction between these guys? This cell over here is going to be, if you have an incoming scene, then you have one S plane. So they call these different S planes. This cell over here might respond to patterns in this region of your input. This cell, the next one, responds to the same pattern, but now in this region of the input, and so on. So they're positionally arranged with identical responses. And when you go across these different planes, each of them responds to a different pattern. So this is the set of S planes within each each group. And now, corresponding to these S planes, now there's a C plane. And what the cells in the C plane too are arranged according to the position in the incoming image itself. And each cell in the C plane responds to a small region of cells in the corresponding S plane. So you have one C plane per S plane. And now, the way the whole thing works is when you consider just the input, this is your image, then within any S plane, each of the cells is going to look at a different region of the input. And the different S planes all look at, detect different patterns. Then subsequently, you'd have several of these S planes in the first block. And then you have some C planes, one corresponding to S planes. This is the first block, where each cell is going to look at an elliptical region of the corresponding S plane. And it responds to the values within that elliptical region. And this is the first block. Now the second block, again, once you're done with this, has a collection of S planes. And now, within an S plane, if you look at any cell, this is going to be looking at some region in the input But just as we saw in the last class, this region in the input corresponds to regions in all of these guys, right? And so this cell would simultaneously be looking at all of these regions. Similarly, this cell, sorry, no, this is for the C plane, this one. This cell is going to be simultaneously looking at all of these regions, but in the C cells of the previous layer, because the C cells have finished the cleanup, right? Similarly, this cell over here is going to be looking at a slightly shifted region for all of these C cells simultaneously, and so on. And then the next C plane is simply going to look at a small elliptical region over here, and it's going to clean it up. So each S plane, each cell in an S plane looks at all of the C planes of the previous layer. Each cell in a C plane looks at just a small region of cells in the corresponding S plane. Yeah.
So in a convolutional network, would this be analogous having multiple filters on the lowest layer rather than just one filter?
So each of these S planes would be one of your filters. And that's pooling, right? So in fact, you're getting to just that. He actually had formulae, right? So if I have a collection of C planes over here, how does this S cell respond? Corresponding to each of these planes, it's looking at a small region, and within the region it has a bunch of weights with which it combines the values within that region of the C cell, the C plane, and adds them up and has a final response. So there's this ugly formula over here. It looks complex, but if you look at it carefully, it looks like a ReLU. Now, so also the C plane over here, this one looks on. Now, unlike the S plane, which looks at all of the previous C planes, any cell in the C plane looks at only a region of the corresponding S plane, just one plane. So there's a one-to-one correspondence between S and C planes. And this one too has a response, which is given by this horrible formula over here. It's not comprehensible, but then if you look at it carefully enough, it actually ends up looking somewhat like a ReLU. So now, because the C planes are cleaning up the response of the S planes, the C planes, so you'd have one S plane, and correspondingly you have a C plane. So a cell over here looks at a region of the S plane. The next cell looks at a somewhat shifted region where the overlap is not very much. So as a result, the C planes are smaller than the S planes. They're just cleaning up what's in the S planes. Now, this means that when you go through one layer, by the time you go from the S to the C planes, the total amount of information is reduced. To make up for it in the next layer, you will have more S planes than in the previous layer. And these S planes will be the same size as the C planes because you have a one-to-one correspondence. But then each of the S planes will now have a C plane, which is smaller than the S plane itself. Then in the next layer, you're going to again have more S planes than you had planes in the previous layer, and so on. So how is the whole thing learned? They used Fukushima suggested a very simple unsupervised model. Again, remember, the human eye really gets no supervision. When you start off as a child, there's nobody giving you labeled data and providing you information, you just learn. So the idea was that if you looked at a collection of S planes in any region, right? And then if you look at a C plane in the corresponding region in the previous layer. So this is the previous block, this is the next block. This cell in the C plane is going to be connected to every S plane, right? And one of these guys, of all of these guys, one of these will have the highest response. So you just assume that this has only activated this one guy, ignore the rest of these, and then just use the simple Hebbian rule. Anybody remember the Hebbian rule? What is the Hebbian rule? They fire together. Those that fire together wire together. So the increment is x times y, right? And so the weight of this connection is going to be incremented by the product of x and y, the input and output. But then once you increment the weight of this one cell, you're going to do the same thing for every other cell in this plane, because we know that all the cells in the plane have the same response. Now, over the entire image, eventually you're going to find that different cells over here, different planes over here respond most to different regions of the different C cells. So eventually all the planes get trained. Now, when they actually implement this, and they implemented this and fed this a bunch of different images, here's what they found. They found that the earliest cells end up learning simple patterns, like maybe if you train the network on a bunch of images of characters. The earliest cells would learn maybe the parts of characters. Then as you go through the network, the patterns that the cells respond to become more and more complex. So later on down, you might have individual cells that respond to entire characters. So you'd have some cells, some S-planes, which are specialized to detecting the character A. Something else might detect the character B, and so on. And so they actually have these very nice results. They show that, Fukushima showed that, for instance, if you train these models on images of lots and lots of digits, by the time you get to the final layer, you have some S-planes fire only in response to inputs of 0. Others fire only in response to inputs of 1, and so on. So they automatically learn to cluster visual concepts, and they do so even in the presence of noise. This is lovely, right? Completely unsupervised. It learns to detect visual concepts. But there's no way of providing supervision over here. This whole thing is unsupervised. So how would you make it supervised? Anybody? So if you were given this model, there's no supervision over here. You're just providing inputs and it learns everything, right? So now I want it to learn specific things. You want to provide supervision. What is the obvious thing for you to do? Pardon me? Labels to what? Because remember, you have many planes coming out. Pardon me? Classification. But you need one more bit, and what is that? One piece is missing. You need a final classification layer, right? But anyway, here's a point. All right, this was easy, 10 seconds. Anybody on Zoom? Okay, someone on Zoom, answer the first question. I can hear you if you speak.
It's true.
And what about the second? Anyone? Also true. Thank you. Can I have some more enthusiasm in the room? You shouldn't put me to sleep. I put you to sleep. All right? Okay. So both of them are true. Anyway, so the neocognitron is fully unsupervised. The semantic labels are automatically learned. How do we add external supervision? So I'm going back to this problem, and I'm going to catch Arjun over here. He's my researcher of the future. He's going to add supervision. How would you do it?
You add like a softmax.
Thank you, right? You need the final classification layer. All you have to do is feed the final output into some kind of a classifier, a softmax, and now you actually get a classification output, and this can be trained, right? And just regular backprop would take care of everything. But there's one distinction over here. What kind of network is this? It's a shared parameter network, right? Because within any S-plane, if you make up an update to one unit, you have to make an update to all copies. So the way we do it, only the S-planes are plastic according to the original model. So even in Fukushima's model, only the parameters of the S-plane cells were learned. The parameters of the C-plane cells were fixed. So over here, that means that you'd have this sequence of S-planes followed by C-planes, and we would learn the parameters of each of these S-plane cells, but not the C-plane cells. Now, we want to make some simplifications. So this was what was done by originally by Jan LeCun. There were several proposals. The one that became most famous, all of them are identical. But LeCun actually came up with an app which was very eye-catching. So that stuck. Now, the original neocognitron has many identical copies of a cell within any plane, right? Which, as we know, is exactly the same as scanning with a cell. You just, instead of having 5,000 copies, you take one cell and try it out 5,000 times. So that's one simplification. The second is these elliptical receptive fields that Fukushima had are kind of hard to model. So you're going to say that the receptive fields are rectangular or square. That's the second simplification. And then third, we're going to say over here, remember, we're going to still stay with the original model. So the way we said it, C cells are cleaning up what you see in the S cells. So a C cell is going to see a rectangular region of the previous S plane, find the maximum value because it's doing a max. The equivalent of C cell, again, this is going back all the way to Hubel and Wiesel's model, right? And then it's going to stride forward because it's cleaned up this whole region, so it can go over a whole lot. Maybe just replicate some of the stuff at the boundary, or maybe not even overlap at all. But as the C cells are going to look at largely non-overlapping regions of the input. So the C cells are basically striding between responses. If you thought of it as a scan, the C cell scans have a large stride. This results in a shrinking or a downsampling of the input itself. And so here's what the response looks like. If you actually consider what happens in the computation, then within, you may have the C cells of the L-1th layer or the L-1th block. And then if you look at any single S cell in the Lth block, this one is going to be looking at a corresponding region from all of these guys, right? So corresponding to each pixel over here, each element over here, there is going to be one weight. So the S cell will have as many sets of weights as you have planes, C cell planes. And within each plane, the weights are going to be arranged in a two-dimensional grid. That is this entire grid, right? So if you look at the equation over here, you're going to have these weights where there are three indices. The first is which plane it's looking at, and the next two is the position within the plane. And to compute the response of the cell, you would just first multiply each weight with the corresponding value in the C cell underlying it, right? And then sum it up. So you have the product of the C cell pixel value and the corresponding weight over the entire rectangle. That's being summed up. So this is summing along the x-axis and the y-axis, and then you sum across all of the planes. And that's going to give you this affine value. And then you will have, of course, an additional bias that's not shown over here. And that's going to give you the affine value at this one position, which would then be put through the activation shown by sigma to give you the response at that position. So that's how the S cells respond. And what about the C cells? The next level of C cell over here is going to simply look at a small region of the S cell outputs and just pick up the maximum. So that's the basic computation. Again, instead of having many copies of the cell, you could just have one cell which sort of scans left to right, which is the scanning we know is, what was the word we used for it? Can you say that aloud? Convolution, that's right. So here's how, so the whole thing is kind of simple. Very simple operations over here. The final layer outputs all just get flattened out and go into a softmax. Or you can have something more detailed. And then the whole thing is trained using backpropagation. So this was Jan LeCun's original demo, where he was trying to recognize handwritten digits. This was a big problem with the postal services in those days. People would just handwrite addresses, and these had to be manually read. They were looking for automated tools. So LeCun was an AT&T, and he built this tool. And you can see how as this thing scans the inputs, it actually very accurately detects the digit that was written. The database that was collected back then was the MNIST database, which you probably know, which is very well known these days. So this is actually from LeCun's website. So the story so far, the mammalian visual cortex consists of S cells, which capture oriented visual patterns, and C cells, which perform a majority vote over groups of S cells for robustness to noise and positional jitter. The neocognitron emulates this behavior with planar banks of S and C cells with identical response to enable shift invariance. Only the S parameters of the S cells are learned. And C cells perform the equivalent of a max over groups of S cells for robustness. Unsupervised learning results in the learning of useful visual concepts. But LeCun's LayNet, so this was LayNet, named after LeCun, added external supervision to the neocognitron. S planes of cells with identical response were modeled by a scan over the image planes by a single neuron. And the C planes are emulated by cells that perform a max over groups of S cell responses. And this whole thing gave us a convolutional neural network. So you see the biological basis of where this model actually came from, right? So here's the general architecture of the convolutional neural network. It comprises convolutional and pooling layers. Convolutional layers are basically the S cells, which have a learned response and look at all of the planes in the previous layer. And the pooling layers are the C cell planes or C cell responses, which look at groups of S cell outputs and pick the max. Typically, a pooling will follow a convolution. Pooling layer will follow a convolution layer, but then you can have multiple convolutional layers before a pooling layer is included, like out here. And eventually, the final layer is going to be a pooling layer, or could be a convolution layer, and that's going to give us a bunch of planes. But then subsequently, we just take all of these values and we flatten them out into one large vector, over which you can just run a simple softmax, or you could have an entire MLP. In LeCun's model, you actually had an MLP. So here are all of the layers, and only these highlighted convolutional layers have learnable parameters. The pooling layers are fixed. They're just picking a max. There's nothing to learn. So what does the convolution layer look like? A convolution layer is going to look at the collection of maps produced by the previous layer. And as I said, each cell over here is going to look at regions of all of the maps, corresponding regions of all of the maps in the previous layer. So within the convolution layer, you have two components. First, you compute the affine values from the outputs of the previous layer, and this is going to give you an affine map, right? So you'll be computing these values from all the positions of the input, and so correspondingly, you're going to get an entire map of affine values. Then each of these affine values is then put through an activation function, and so then you're going to get an activation map over here. The affine map has corresponding to it these filters, and these filter parameters are learnable. So let's look at the affine map first. If you look at this affine map, to compute any value over here, you're looking at all of the maps in the previous layer. So let's look at what would happen. What is the contribution of just one of these maps to this affine map? Now, in order to compute, this is one of the S-planes, right? There are several of these. So in order to compute the response from all of these, this affine value is the sum of the responses from all of the planes in the previous layer. Let's see just what one plane is going to give us. Corresponding to that plane, there's going to be a set of weights, as I saw. And so in this example, I have a 3x3 filter. It's the S-plane is looking at a 3x3 region of the previous layer. And let's just assume that this guy over here represents this one plane in the previous layer. Now this is a neuron, right? A perceptron, regardless of how I'm talking about it. An affine value has a bunch of weights. It also has a bias. Do not forget the bias. But let's just assume that the bias is 0. So what we would do is just place this filter on top of the map as shown here. And if I can get this thing to play, in the figure, the little red number shows the actual filter weight. And the large number shows the value of the map underneath. At each position, you'll be multiplying the filter weight with the map value underneath. So you're going to get one product for each of these 9 positions. You sum them all up, and that's going to be the final response. So you see 1 times 1 plus 1 times 0 plus 1 times 1 plus 0 times 0 plus 1 times 1 plus 1 times 0 plus 0 times 1 plus 0 times 0 plus 1 times 1. That's 4, right? So that value is 4. And then you would step forward by 1 and compute the same value at the next position. And do this as you go through the input, as you scan the input. And that's how you compute the contribution of this one map to the one input map to the output affine map. But then, of course, that was just the contribution of one of these guys, right? But in order to compute this, this is simultaneously looking at all of these input planes. So it's corresponding to each one of these. It's going to have a set of 3 cross 3 weights. Now, all these weights can be different. They are not identical. This set of 9 is not the same as this. You will have a different set of weights corresponding to each one of the input planes. And so to compute the value, this one is going to be placed, that set of filter weights is going to be placed on all of these planes like so. And then you compute a component-wise product and then sum them all up to get this one value. And then the whole set is going to slide by 1 position. And you repeat the process, component-wise product and a summation. And you do this all the way left to right. And then again, don't forget that there's a bias, right? So at each position, the z value that you would compute is given by placing this filter at that position of the input, performing a component-wise product of the filter value and the underlying input value, and summing this up across all, not just over the region of the filter, but also across all the maps. So that is this equation over here. This inner product is the product of the weight and the input at one position. You're summing this over the entire surface of the map of the filter, and this final summation is across all of the maps. This clear to everybody? Right? Okay. So how many weights? Suppose I'm using, suppose I have like 10 input maps and my filters are 3 cross 3. Then how many weights will I have in total? Anyone? How many will I have in total? So I'm trying to compute this one value from all of the inputs. And the filters, there are 10 of these guys here. And the filter face is 3 cross 3. How many parameters would I have? 90 plus the bias, 91, right? Now, suppose I want to compute the second map. Corresponding to the second map, I'm going to have a different filter, which is, again, a bunch of 3 cross 3 values, 1 per plane. And these are completely different from the first set. And these would now be placed on the input and scan the input. And that's going to give you the second map, right? And so eventually, you're going to have one such for every output map, right? Now, viewing this in this manner is a bit of a pain. So it's much more convenient to say that I'm going to just stack all of these guys, all of the inputs, into a 3-dimensional cube. And then if I stack them as a 3-dimensional cube, this guy over here is just representing a stacking of all of these input planes. Then the filter, again, is now going to end up becoming a 3-dimensional cuboid. And to compute the output, I just place the filter against in this position of the input. You perform a component-wise product of the filter values and the underlying input values over the entire region covered by the filter. So first, that term is given here, this inner product. This inner term is showing you the computation that's done for one of these planes, and this outer term is summing over all of those planes. And that's just going to give you one value over here, right? And then this whole entire filter is going to scan left to right to compute the output map. Now you would have, so for every output map, you would have one such cuboidal filter. Make sense, right? Nate, I see a question on your face.
Oh, I got many, but no, nothing specific.
Okay, nothing specific. All right.
I've been thinking we need a new math notation for this.
All right. So now, the size of the output depends on various factors, including the size of the input and the size of the filter, and may not be identical to the size of the input itself. So let's take a brief look at one of the issues over here. Let's say my filter is 3 cross 3 and the input is 5 cross 5, and I scan the filter left to right, but I'm not allowed to go past the edge. Then what is the output size going to be? 3 cross 3, right? I have this one position, then I can step one forward, and then I can step one forward, and then I'm off the edge. So in general, if I have, this is going to be 3 cross 3, right? In general, if I have, what happened to my chalk? Why does my chalk wander? Yeah. Let's say I have, say, an n cross n input, and if my filter is m cross m, then how many do I have remaining over here? N minus m, right? So I can take n minus m steps forward, but then I also have this initial position where I placed it. So you're going to have n minus m plus 1 on each side, and so your output is just going to be n minus m plus 1 on each side. You're going to lose, if your filter is m wide, you're going to lose m minus 1 columns. If it's m deep, you're going to lose m minus 1 rows. And so this results in a reduction in the size of the output corresponding to the input. And sometimes you don't really want to do this. You just want to have a one-to-one correspondence so you can maintain the size. And to handle that, very often we just like to pad the input with zeros. Not the output, you pad the input with zeros. This lets you go off the edge, right? And so I'm losing m minus 1 columns, right? To compensate for it, I must add m minus 1 columns of zeros to the input. And I will distribute these as uniformly as possible on either side of the input. So also I'd be losing m minus 1 rows. So I'm going to add m minus 1 rows of zeros distributed above and below the input. And now, because I've added these extra m minus 1 rows and columns of zeros, the output size is going to be m cross m. So once that is done, you have this affine map. And then you're going to apply an activation pointwise to get the final activation map. This is very easy. So if I were to write some code, here's what you would do for each layer of your convolutional network. Within the layer, you're going to be scanning left to right, top to bottom, and then you're segmenting out this 3-dimensional region of the cuboid. And then your filter is also going to be correspondingly 3-dimensional. So you just have computing a tensor in a product which is going to give you one value, and maybe you add a bias, and then you apply an activation to it. That's going to give you that one value. And then you're scanning left to right to get the entire new map. And this you would be doing for every filter. I think this is being shown. I just written a tensor notation. You'd be doing this for all of your filters simultaneously. So in summary, convolutional layers scan the input using a bank of filters. A filter is just a neuron in a scanning layer. Each filter jointly scans the maps of the previous layer to produce an output map. So you get as many output maps as filters. And you may have to pad, and this is regardless of the number of input maps. The number of output maps depends on only on the number of filters, not on the number of input maps, right? And then we may have to pad the edges of the inputs with zeros to ensure that the outputs have the same size as the inputs. Questions? Yes.
Is it a better number to pad with instead of 0? Because
You're not, anytime you give it anything other than 0, you're presuming there's some information over there.
if you're putting 0, you're probably also
You're assuming there is nothing, there's no information to be had. So that's about it. I mean, you can,
reducing the weight of the cells on the corners on the edges.
it's a good question. You can test it out. You can try to see if those can be learned. Right? That's a good question. Easy to try. Good time. Okay. I don't have an answer, but you will provide us one, right? Everybody remember. Okay. Now the other concept here is pooling. What do we do for pooling? These pooling layers may intermittently follow these convolutional layers. They don't necessarily have to follow every convolutional layer. But here's what you do. Again, you have a little region. The pooling is going to be looking at a small region of the input. And if you're performing max pooling, within that region, you just pick the maximum value. So here, for example, you're going to be picking the value 6. Now, the way LeCun implemented it, pooling filters strided by more than one pixel at a time. But one of the inconveniences of thinking of it in terms of striding over larger inputs is that when you begin looking at derivatives and computing derivatives and such like, this is going to give you a head spin. So it's much more convenient to think of everything as always striding by one element at a time, because that's a very convenient way of thinking about it. So if I think of it along those terms, then this is what pooling will look like. Within each window, it's going to pick just the largest value and copy it over. And the output is going to be approximately the same size as the input, except for some edge effects, right? So the two layers are pooling and convolutions, where in every case, you're just striding one at a time. In the case of convolution, you're summing over all of the input planes. In the case of pooling, each pooling is performed over just one plane. So you're going to get one pooling output layer per input. So in the case of convolutions, the number of output layers is going to depend on the number of filters, not on the number of inputs. In the case of pooling, the number of output layers is going to be exactly the same as the number of output planes is going to be exactly the same as the number of input planes, right? Now, you don't necessarily have to perform max pooling. You could also compute the mean. There are different statistics to compute. You have a question? Yeah.
Yeah. How do you do backpropagation to the max pooling layer?
We're going to get to that, right? Right. So we won't be dealing with backprop until the next class. But you can replace max with other statistics, like a mean, in which case you'll be going left to right and computing the means of the numbers within the region. So here, when I'm performing max pooling, observe something interesting. For max pooling, I first found the location of the maximum value. And then I just copied the value of at this maximum location. So I kept it as a two-step process. There's a reason for this that we will get to in the next class. In the case of mean pooling, I just compute the mean and copy it over, position by position. But then you can have other kinds of pooling. You can have a p-norm, which is some generalization of the mean, right? Or you can even have a little neural network which decides what is the best thing to compute from this collection of values, in which case this becomes a learnable operation by itself. So pooling layers scan the input using a pooling operation. For example, by selecting the max from a k cross k block of input, each pooling filter scans scans individual maps or an individual map in the previous layer to produce the output pool map. So you get as many output maps as input maps. For pooling, we generally do not pad the edges because it makes no sense to say what is the maximum of something and 0. The 0 is providing no real useful information. And throwing in a whole bunch of zeros to compute a mean is also equally meaningless. So we do not usually pad, which means that pooling will always shrink your input by a little bit, right? So far we've only considered layers where the output size is approximately equal to the input size. And I said that we want to do this, we always want to assume a stride of 1 because that simplifies matters conceptually, right? Now, but there are two other operations. One is the so-called downsampling layer, where the output is explicitly smaller than the input. In a downsampling layer, if I'm downsampling by S, I'm going to drop every S minus 1 rows of every S rows and S minus 1 columns of every S columns. So if I were to be downsampling this by a factor of 2, this is the equivalent of saying that I'm setting every second column to 0 and every second row to 0, and then I'm throwing them away. So this is what downsampling will do. Was clear to everybody? Right?
Usually do we do it like this, or do we like do a main max average something and find a smaller value, like combine the values of 4 pixels and find a smaller value?
That's mean pooling, right?
Yeah. So do we do downsampling like that, or do we just actually drop the values?
This is, when you do this, the stride over here has nothing to do with whether you're downsampling or not.
Yeah, for sure.
So this you can imagine as just being done with a stride of 1. Downsampling is an independent operation. Don't confuse the two. Okay? So that's going to cause you grief when you begin talking about backpropagation. All right? But to answer your question, this is downsampling, right? I'm just throwing away S minus 1 rows of S rows, S minus 1 columns of S columns. So this is just some pseudocode. You're just throwing away bunches of things. You're taking a stride and only copying those over. So you need new indices for the output than for the input. But then to answer your question, downsampling usually follows some process. So downsampling may happen after a convolution, or it may happen after pooling. So in that case, you can just combine the two. And you can say it's convolution with a stride or pooling with a stride. So in the case of convolution with a stride, you do something like this. If you had a downsampling by 2 over here, then you'd perform a convolution at this point. Then you're going to step forward by 2 and compute the new output. Similarly, step down by 2 and then step forward by 2. But then regardless of this, even though you had performing a convolution with a stride, it's much more convenient and much more intuitively simpler to think of it as a sequence of 2 operations, where you're just doing a regular convolution with a stride of 1 and then dropping every other element. And particularly when we're performing backpropagation, this is going to make things much simpler. Right? So when we do this, if the input is n cross n and you're striding by some size s, instead of the earlier one of n minus m plus 1, you're going to have n minus m over s plus 1 because you're striding by s on either side. So there's just some pseudocode. Similarly, in the case of pooling, you could be pooling and then downsampling, or you could just be pooling and striding with a step greater than 1. And so here again, if you were taking, if you were pooling and then downsampling by 2, that's the equivalent of pooling with a stride of 2. But then once again, it's much more convenient to think about it as pooling with a stride of 1, because pooling is basically convolution with a nonlinear operation, right? Which is a max. If you were performing a mean, it's convolution with a linear operation, and then followed by downsampling. So although in an actual implementation, you just have a stride in the pooling code, conceptually, it's more convenient to think of it this way, right? So this is going to be performed separately for every map. Yeah.
It's technically right. Let's say, because it really would depend on how, like, make those two equivalencies, like the pooling with the stride versus pooling plus downsampling. Isn't it technically, it has to depend on how you downsample.
You're just dropping things, so it's going to be exactly the same.
But if you selected, for example, if you downsample, say only the top left of a layer, for example.
It doesn't matter, right? If I'm striding by 1, I'm just computing values I'm never using.
Okay.
You're throwing them away. That's about it. So anyway, again, if you're downsampling, anytime you downsample by a value d, yes?
In what cases is downsampling useful?
We almost always downsample after pooling, and very often after convolutions too, right? So we'll get to that if I have some. Repeat that question to me if I have time at the end of the class, okay? Please, yeah.
Solid and resonance by adding residual connections.
Yes, but there's more to it than that. You have to be careful, okay? There's another operation you can do. I can reduce the size. Actually, let me answer your question. So if I've got an image, and if I want to classify the image, then if I'm not downsampling this, I'm starting off with, say, a 10 cross 10 image, right? And I never reduce the size. Eventually, I have 1,000 filters in the final layer. What is the output I'm getting? I'm getting 1,000 times 10 cross 10. Do I really need that much information? Just those 1,000 numbers is still has far more information than, or has far more numbers representing the input than just the 100 numbers I had originally, right? So you're going to have a great deal of redundancy as you go through the network and you increase the number of filters. You compensate for it by just reducing the size of the maps. Right?
But if pooling layer reduces the size of the output of one layer, then why do we need to downsample it? Because we'll already get some lesser output as compared to.
So where did we say, if you're pooling with a stride of 1, are you really reducing the size of the output? Remember that I'm asking you to think of pooling as an operation everything is an operation done with a stride of 1, which is separated from downsampling. Don't conflate the two. Downsampling is different from pooling, right? There's a common problem in the general presentation of these ideas that they just conflate it and it's one common thing. It's not. They are two different operations. One is pooling, the other is downsampling, right? So any other questions? I'm reducing the size of the maps. I could be doing something else. I can also be trying to increase the size of the maps, right? So how would I do that? I'm just going to stick zeros between every alternate rows, between adjacent rows and adjacent columns. So if I want to upsample by 2, I'm going to introduce one column of zeros between adjacent columns and one row of zeros between adjacent rows. If I'm upsampling by 3, there'll be 2 columns of zeros and 2 rows of zeros. Now, upsampling is generally followed by not a CNN, but a convolutional layer, right? And it's usually not useful to follow it by a pooling layer, because if you're upsampling by 3 and then pooling, you're getting nothing useful. You're just going to get a bunch of zeros. So upsampling is also not useful as a final layer of a CNN. Introducing a whole bunch of zeros for no purpose buys you nothing. But so upsampling, literally, I'm calling it dilate, is to say I'm going to expand my image by a factor x and introduce zeros in the newly introduced inserted rows and columns. Now, practically speaking, you can say upsampling is typically followed by convolution, and we like to think of it as convolving with a fractional stride. So if I'm upsampling by 2 and then convolving with a stride of 1, the result is larger than the original input by a factor of 2, right? Which is the same, which is like saying every time I step forward by half a pixel. So you like to think of it as convolution with a fractional stride. Now, so these are the 2 resampling operations. In summary, map sizes can be changed by downsampling or upsampling. Downsampling drops s-1 of s rows and columns. Upsampling inserts s-1 of zeros between every 2 rows and columns. Downsampling typically follows convolution or pooling, so it reduces the size of the maps. Upsampling occurs before convolution. It increases the size of the map and does not generally occur before pooling layers. So the story so far, convolutional neural networks are supervised versions of a computational model of mammalian vision. They include convolutional layers comprising learned filters that scan the outputs of previous layers, and pooling layers that vote over groups of outputs from the convolutional layer. Convolution can change the size of the output. This can be controlled via zero padding. Pooling may perform max, p-norms, means, or be learned. Resampling layers increase or decrease the size of the map in a proportional kind of manner. And so downsampling can be merged with the preceding convolutional pooling operation by simply performing the scan with a stride greater than 1. Upsampling must occur before convolution operations, right? So there's a pull. I'll give you the full minute for this one, but it's a little more detailed. Okay, 10 seconds, guys. Okay. Can someone on Zoom answer question 1? Someone on Zoom? Is nobody on Zoom? 1 and 3, okay. I can hear you, so you can actually say it. So anybody on Zoom, question 1?
One and 3.
Thank you. And over here, let me pick up a random victim over here. So you there, what's your name? Chloe? So what is the answer to question 2? 2 and 4, right? Good enough, perfect. So you get it. So let's put all of these things together for a typical image classification task. I'm going to be assuming max pooling, right? So if you wanted to train an image classifier, you typically get either grayscale or color images. I'm going to assume color. So the image like this would actually have a red, a green, and a blue. So the input is actually 3 pictures, which I can stack together into a cube as before. Now, here is some terminology. When you have multiple of these planes, the more recent terminology that has been introduced in recent years is to call them channels, following the terminology that is used to describe images. These are called color channels when you're speaking of images. So this terminology has actually extended, but the channels basically represent the individual S-planes in my output, right? So, and you're going to have 1 channel per filter because each filter is computing 1 plane. So now the input is going to be 3 pictures, which I can represent as a cuboid. And then you begin with some set of filters, let's say K1 of these guys. And so let's assume that each filter is an L cross L filter. So they're going to be, the actual size of the filter is L cross L times the depth, which is 3. And the number of filters typically is chosen to be a power of 2 for various historical reasons. It kind of works. And the filter widths are typically 3 cross 3, 5 cross 5, or even 1 cross. You want these to be small enough to capture fine features, particularly if you're scaling images down. But what is this 1 cross 1? Does anybody remember what this could be? Pardon me? We talked about this extensively in the last class. It was half of last class. When I didn't have a distributed scan, how many pixels were you considering from each input? 1, right? It's like picking 1 from each plane, right? So this guy is a non-distributed scan, 1 non-distributed layer in your network, right? So, and you're scanning NLP. Just to give you an idea, don't get confused. It's not like, it's a non-operation. It's like scanning with a non-distributed. layer. So now it's better to call these 5 cross 5 with a parenthesis, 3, just to say that the number of channels is 3, right? These are all filters that you would be learned. These are all parameters that you would have to learn. So the total number of parameters you'd want to choose is how many filters, what is the span, and if it's downsampling to, what is the stride, S, when you're convolving. And now, of course, each of the filters is going to have 3L squared over here because it's now 3 channels. And what is this 1 for? The bias, right? And K1 of these guys. So those guys are going to give you a bunch of output affine maps first. So this is just the equation that we had earlier for computing the affine maps. And those affine values are put through the activation to give you the final output maps for the first layer. Let me just and all of these parameters must be learned. Now the next thing you would do, assuming that I'm always pooling, is to subsequently have some kind of a pooling layer, which is maybe striding with some stride D. Again, this is actually pooling with stride 1 followed by downsampling, right? So that's why I'm using the D for downsample. And that's going to result in a collection set of smaller maps, one per activation map from the previous layer, right? Now, how is pooling done? At each position, you're picking up a small region of the input and you're taking the largest value. So you'll be looking at some, you'll be saying, here is the range of X values, here's the range of Y values. I'm going to be picking the largest value within it, and you just pick the largest value over here. But you don't typically just do it this way. What you would do is to break it down into 2 operations. So the parameters to choose is, what is the size of the region you're going to be looking at and how much you're striding by. But more importantly, you decompose it into 2 operations. The first step is to say, within this window, which is the position of the element that is the largest in value. You would record this term, the position of the largest value. And the actual pooling would just read the value at this position. And when we begin speaking about backpropagation, you'll see why this is important, right? So that's going to give you a whole bunch of downsampled pool planes, right? Then at the next step, so again, jargon, filters are also often called kernels. The number of individual filters are called channels, as we saw. This is based on the notion that colors are channels in an image. So that comes from computer vision. And so the number of filters is always the number of output channels. You're going to have as many output channels, as many output planes as the number of filters, right? And then the next step, you're going to have a bunch of new filters. But say I have each filter has a phase. Suppose I have K1 filters in the first layer, first convolutional layer. And then I have a filter in the convolutional filter for the next layer, and I've decided that its phase is 3 cross 3. How many parameters will the filter actually have? I have K1 filters in layer 1. In layer 2, the filter face is 3 cross 3. How many parameters will it have? How much? 9K1 plus 1, because the depth is going to be K1, right? Why is everybody so quiet? So did 9K1 plus 1 make sense to you guys, right? Okay. And so those are the parameters that we're actually going to be learning. So the parameters to choose is how many filters you're going to have in this layer, the size of the face, right? And the stride. And then the parameters that you'd have to learn are going to be the number of filters times L squared plus 1 times, so this is K2 is the number of channels, right? So for each filter, you're going to be learning K2 L3 cubed plus 1 parameters. Number of channels times the phase plus the bias. And that's going to give you, that operation would give you a bunch of output channels, which are then going to be downsampled again. You'd repeat this, and here, of course, again, you'd have to figure out what is the size of the region over which you're performing the pooling, how much you're striding by. Do that a few times and eventually you're going to end up with a final output. Those are going to be flattened, and then you would have a final MLP. And so more parameters to choose is the number, how many layers the MLP is going to have, and what is the width of the layers. So each convolution with stride 1 typically maintains the size of the image with appropriate zero padding. Without zero padding, it's going to lose something at the edges. Each convolution layer will typically increase the number of maps. So why are we trying to do this? So let's say I have an image which is 32 cross 32, and it has 3 channels. It has 3,000 numbers, right? Now, if I want to retain all the information about the image, what is the minimum number of numbers that I will require at each layer to be output by each layer? Can somebody say that aloud? 3,000, right? Anytime the number of values is lesser than the number of inputs going in, you have lost some information. Correct. So when I perform a convolution, my first convolution is going to give me a bunch of planes. So let's say I'm not losing anything at the edges. So if I have an input of 32 cross 32, the depth doesn't matter, right? So then each convolution is going to give me an output which is 32 cross 32. I need at least 3 of these guys to retain all of the input, right? But then I assume that at the next pooling, I plan to stride by 2. What will the size of the output be? It's going to be down by a factor of 4, right? So have I lost information? Right? I have. How would I compensate for it? Can you say that aloud, please? So you increase the number of channels, right? And the number of channels, you would have to think about this. You'd have to consider what you're going to be doing downstream when you decide the number of channels. So if I want to retain all the information, and if I'm going to be striding by 2, I'm going to be losing a factor of 4 in the downsampling operation. To compensate for it, the number of channels has to increase by a factor of 4 also, right? Unless I'm happy with losing information, which you might be in some cases. And so as you hear.
I have a question. So when you say like to increase or like to, I guess like you're losing information when you're downsampling, and to like get that information, not get that information back, but you want to increase the number of filters you have. Yeah. Which then increases the channels. Is that what? Yeah.
So exactly right. So just to give you an idea, let's see this pictorially. So let's assume that I just have something which is 4 cross 4, or so this is just 4 cross 4. This is my input, and let's say I just have 2 of these channels, right? 2 of these guys. Then if I use a filter, assume you have no edge effects, so you're padding the boundaries. Each filter, what is the size of the output of each convolution going to be? Over here. Come on, guys. I have successfully put you to sleep. Okay, can everybody say aloud, what is the size of the output going to be if I just perform a convolution? Same. Give me a number. Say it aloud, everybody. Thank you. I'll make you say it even louder if you sleep on me, okay? So this is going to be just 1 filter, right? Output. Is this retaining all the information here? Guaranteed not. I have fewer numbers. So how many filters would I need out here to retain everything? I need at least 2. As many filters as the number of input channels, right? But then assume that at the next step, I'm performing a max pooling and I'm downsampling by 2, right? What is the output here going to be? 2 cross 2, right? Does this retain all the information going in? So what do I need to do over here? I need, how many more would I need? 8 total. I need 8 of these to retain all the information there, correct? So how many channels will I need here? 8 also, right? And so this is something that you'd have to keep track of. As you go through the layers, typically the number of channels you will have is going to increase because you plan to be downsampling by pulling, with pulling after each layer. This is just a natural consequence of trying to retain as much information as you can. Is that making sense to everybody? Right? So as a result, you will find this, that increasing the each convolution layer will generally increase the number of maps from the previous layer, just so that you lose the minimal amount of information. And of course, each pooling layer decreases the size of the maps, and so this loses some information. Within the layer, filters must all be the same size, but the filter sizes may differ from layer to layer. So the first layer filters may all be 5 × 5, the next one may be 3 × 3, the next one may be 1 × 1, it doesn't really matter. So, and the parameters to choose at each point is how many filters, what's the size of the filter, what is the stride, and all of these are interlinked and also must reflect your decision on whether you're happy with losing information or not. Okay. So there's a final poll. This is a 30-second poll, and then we'll just rush through the rest. Okay, 10 seconds. Does anybody want to answer the question? So what is the neuron? Again, I put the term neuron over there for a reason. What was a neuron? Going back to the scanning MLP. Why each one of our filters represented a neuron, did it not? Make the connection? So what is the relationship between the number of channels and the number of neurons in the corresponding scanning MLP? They are the same. Make sense? Right. So, and so here was the example of the architecture for digit classification used by Jan LeCun. He had 5 × 5 convolutions, 5 of those, downsampled by 2. Then he had, I think, like 20, a whole bunch of these, 10 of these, downsampled, flattened it. Anyway, so how do we train this network? You have this entire collection, right? And this training is very similar to a regular MLP. The only difference is in the structure of the network. You're going to provide, as before, examples of training data where each instance is going to be maybe an image and a class and the corresponding class. You're going to define a divergence between the desired output and the true output. And the network parameters are trained through variants of gradient descent, where gradients are computed using backprop. So here are all the parameters that are learnable, the filter parameters and the parameters of the final MLP itself. So you would start off by passing your training data again. Remember, here's your problem setup, right? You have a collection of training instances. Each one is a data instance and the corresponding label. You want to compute the output of the network for each instance, which is to say you pass the data through the entire network. And then for each instance, you compute the divergence between the current output of the network and the desired output. So that would be the divergence here. The average divergence over your batch is what you're trying to minimize. And so you want to compute the derivative of this average, this loss with respect to each of the network parameters. And then once you do that, you're just going to use standard gradient descent. So none of this is new. The real problem is how we're going to compute these derivatives. Now, as before, you need to only worry about how you're going to compute the derivative of the divergence with respect to parameters for a single instance. So let's focus on that, this one. Now, for a single instance, when I pass the data through the network, eventually the final bit are these flattened, the MLP, after the final output has been, the final convolutional output has been computed. And for MLPs, we know exactly how to perform backpropagation and compute derivatives. So we can assume that we've gone all the way back and we've got derivatives at this point. But the derivatives over here are for a flattened layer, but that layer was obtained by flattening these maps. So you can fold the derivatives back into the shape of the inputs that were flattened to create that vector. So which means that you now have the derivatives with respect to the outputs over here. And all we have to figure out is how to compute the derivatives going backwards from there, and that's going to be the topic for the next class. Right? But once you do that, you can just embed it into gradient descent. So the story so far, just to finish, convolutional neural networks are supervised versions of computational models of mammalian vision. They include convolutional layers comprising learned filters that scan the outputs of the previous layer, and pooling and downsampling layers, although you have to think of pooling and downsampling as separate operations. The parameters of the network can be learned through regular backpropagation. We'll continue that in the next class. Thank you.